In the next problem, we are asked to find the Madelung constant for an infinite linear ionic chain. Madelung constant is nothing but the lattice sum of the geometrical factor in the lattice sum in the Coulomb potential interaction. So, you have positive and negative terms in a linear ionic lattice such as this, for example, sodium and chlorine, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. That is a typical linear lattice that goes on. It is an infinite lattice. So, if we want the Madelung constant, which means that we take out, factor out the terms involving the electronic charge, the distance and so on, express only the geometric ratio. For example, between near neighbors it is 1 unit, and then between the next distance is twice this. So, it is minus half because of the inverse distance, the dependence of the potential on the inverse separation. So, the next one is a positive term, repulsive term between like charges, sodium plus and sodium plus, minus 1/4 plus etcetera, and that is, as you can recognize, this is nothing but the logarithmic series of 1 plus x, where x is also 1, log 1 plus x is 1 minus x by 2 plus x square by 3 etcetera. So, this is just log 1 plus 1, which is log 2. That is the Madelung constant. Next problem is a rather interesting situation, which is associated with the fact that the hydrogen bonds in the ice have two positions. If you consider water molecules in ice, you have 2 hydrogen atoms and 1 oxygen atom. And so, I have an OH bond and another OH bond. Now, in a hydrogen bonded network of ice, this hydrogen atom links to another water molecule here, and so on. It is a network of hydrogen bonded network. They are all different atoms here and so on. So, this has 2 things like this, and this has all the tetrahedral angles. And so on. The structure is extended in 3 dimensions. Now, there are 2 ways of distributing the 2 hydrogen atoms per oxygen atom over the 4 bonds. There are in all 4 bonds to the near neighbors, because it is a tetrahedral structure. So, there are 4 bonds, different ways of distributing 2 hydrogen atoms, per which 2 hydrogen atoms for each oxygen atom, they have to be distributed over the 4 bonds. So, this gives rise to a certain disorder. Associated with this disorder is an entropy. So, this is a 0 point entropy, because even at absolute 0 this disorder persists, because it is essentially a structural disorder associated with the number of different ways of distributing 2 hydrogen atoms over 4 bonds. So, in a, if there are n water molecules, then there are 2n hydrogen atoms, because each oxygen in the water molecule has 2 hydrogen atoms. Therefore, there are 2n hydrogen atoms in the total. Now, we have to find the disorder associated with distributing these 2n hydrogen atoms. Now, associated with this disorder, if this number of ways of distribution is W, then the number of ways of distributing these hydrogen atoms. Now, if this is the number of ways, then the famous Boltzmann formula for the entropy is known as Kb log W, S equal to Kb log W. So, we find the number of ways and then multiply Boltzmann constant, this is the Boltzmann constant. We take the logarithm of the number of ways W and multiply it by the Boltzmann constant, and that gives us the entropy associated with this. So, let us calculate this now. So, we have two positions for each hydrogen atom. So, there are 2n hydrogen atoms. So, the total number of ways possibilities is 2 to the power 2n, but we have only 2 hydrogen atoms to be distributed among 4 positions. So, the total this is not, all these are not available. So, we have a combinatorial problem of distributing 2 hydrogen atoms among 4 bonds. So, the total number of ways is 4 C naught plus 4 C 1 plus 4 C 2 plus 4 C 3 plus 4 C 4. These are the total number. There are 4 bonds. I need not put any hydrogen atom, that is 4 C naught. I can put one hydrogen atom over these 4 bonds, that the number of ways is 4 C 1. This is 4 C 2 is the number of ways of putting 2 hydrogen atoms in among 4 bonds, 4 C 3 and 4 C 4. This is the total number of ways, of which we only get the possibility of distributing 2 hydrogen atoms over these. So, it is 4 C 2. So, it is the ratio of these together multiplied by the total 2 to the power 2n, which gives you W. And this ratio, as you can readily verify, so this will be 2 to the power 2n times 3 by 8 to the power n. This will be 2 square. So, 4 into 3 by 8 to the power n, and that is 3 by 2 to the power n. So, the entropy S is Kb log 3 by 2 to the power n, which is n Kb log 3 by 2, and n Kb is nothing but the universal gas constant R. So, it is R log 3 by 2 per mole. So, putting in the value of R, we get it as 0.806 calories per mole degree K. Calories per mole degree K. That would be the residual entropy of ice. Even at 0 K, this entropy, this amount of disorder and the associated entropy persists. we will continue with our problem solving session today. The problem that we have to solve now is to determine the isothermal bulk modulus and the lattice energy per ion pair for sodium chloride, given that the repulsive potential varies as the inverse 9th power of the nearest neighbor separation and that the Madelung constant is 1.748. We already saw what is the Madelung constant. It gives you the lattice sum for the Coulomb potential with terms of alternating signs. So, for a face centered cubic lattice of the sodium chloride solid, we can calculate the Madelung constant, and that has been given as 1.748. So, the isothermal bulk modulus B is minus V dP by dV at constant temperature, where at t equal to 0, our calculations are all at absolute 0. So, we have P, the pressure is just minus du by dV, where u is the internal energy. Therefore, we can write this as V d square u by dV square. And here this V is n times V, where n is the number of atoms, and we also have the equilibrium, the internal energy U is n by 2 times U, because U is the energy U, internal energy per ion pair for sodium plus and Cl minus. So, this is what we have, and therefore, the bulk modulus can be calculated as for the face centered cubic structure half into 1 by root 2 into 2 by 9 r into d square u by d r square, taking the relation between the r, the atomic radius, the ionic radius, and the volume of the unit cell. So, this is at r equal to r 0. This is something that we can get by setting the by minimizing the energy, where u itself is A e square by r 0. This is coming from the form of the Coulomb potential times m minus 1, where A is given in the problem as 1.748. This is the Madelung constant, and in the problem the index m is also given to be 9. So, we will use that later. We will right now write it just as m and solve everything. So, the bulk modulus becomes m minus 1 into 18 A e square by r naught square when m is 9. So, that is the bulk modulus. Concerns the cohesive energy of copper, an FCC structure, face centered cubic structure again. We are given that the bond energy between two copper atoms is given to be 56.4 kilojoule per mole. And how do we calculate this? We have to remember that it is a face centered cubic structure. So, we have number of bonds is number of neighbors near neighbors divided by 2. So, this is number of neighbors in a FCC structure is 12. So, it is 12 by 2 which is 6. And the energy per bond is given as this. Therefore, cohesive energy is just 6 times this, which is 338.4 kilojoule per mole.